Hello. This lecture will cover pages 230 through 234 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 12L, Series Resonance and Quality Factor. This will be the last lecture in Chapter 12, and I'd like to finish it up with Series Resonance. We're going to start our lecture notes on page 230. Before we begin the discussion on resonance, I'd like to review how x sub c and x sub l vary with frequency. If you remember, x sub c, the capacitive reactance, was inversely proportional to frequency. So as frequency got higher and higher, the capacitive reactance got lower and lower. And as frequency goes lower and lower, the value of the capacitive reactance went higher and higher, because x sub c was equal to 1 over 2 pi fc. If you also remember, the inductive reactance was directly proportional to the frequency, because the formula said x sub l was equal to 2 pi fl. So as frequency increases, the inductive reactance increases, and these were both reactances in ohms. If you take a look, I'm going to plot in the vertical axis here reactance, both capacitive and inductive reactance. And in this abscissa axis, the horizontal axis, I'm going to plot frequency. I think you could take a look from our equations up above that as frequency increases, the inductive reactance is linear and it increases in a linear fashion. As frequency increases, the capacitive reactance is hyperbolic. It's not linear. It's governed by this equation up here. But be that as it may, it gives you this shape right here. It's real high at the low frequency, and at the higher frequency it gets smaller and smaller. The point at which they're equal in a particular circuit, the point at which x sub c is equal to x sub l, it's a very important frequency, f sub 0, and it's referred to as a resonant frequency, and it's in hertz. And we know that omega 0 is equal to 2 pi f, so omega 0 defined by the resonant angular frequency in radians per second. If you look at a simple series RLC resonance circuit at resonance, here we have a forcing function. It's a steady state sinusoidal. We should represent it as a phasor, V sub s, a source voltage. And we have a series resistance, capacitor, and inductance, RL and C. I want to take a look at the total impedance looking into that circuit. And we know what it's equal to. The total impedance in terms of j omega, looking into the circuit here, we've done this previous chapters, is R plus j omega L, inductive reactance, plus 1 over j omega c, which is the capacitive reactance. Well, I'm factoring out a j here, but before I do it, I rationalize this last term. If I take this times a j and that times a j, just in that last term, I think you'll see that j is a square root of minus 1. So at the bottom of the denominator, I get a negative 1. At the top, I get a plus j. So that negative can get distributed to the top. So what I end up with if I factor out a j from these two terms here, just factoring out a j from the reactance terms, I get the impedance looking in there is R plus j times omega L minus 1 over omega c. That's where the minus comes from, in that minus j. We said capacitive reactance was always a minus j. Well, that's the reason. Because we end up rationalizing taking the top and the bottom times j, and we end up with a negative sign in the numerator, incidentally. At the resonant frequency, these two are equal to one another. So at the resonant frequency, whatever that is, these two are equal to one another. So this whole term becomes 0, and I want you to notice two things happen. First of all, what frequency is it that these two quantities are equal to one another? Well, when x sub l is equal to x sub c. When the inductive reactance is exactly equal to the capacitive reactance. Well, you can set the two equations equal to one another, and we're just going to call that frequency omega 0, the resonant frequency. I set these equal to one another and I solve that, you can see that the frequency at which that happens is 1 over the square root of LC. Very important formula. And since omega is equal to 2 pi f, this equation also holds true. F sub 0 in terms of hertz is 1 over 2 pi, the square root of LC. So here's two equations you definitely want to have written down. This is the resonant frequency in radians per second, and this is the resonant frequency in radians per second, and this is the resonance frequency in hertz. The second thing I want you to notice when these are equal to one another up here is the impedance becomes purely real. So the impedance at the resonant frequency is simply equal to the value of R. So looking at this circuit up here, when this circuit's at resonance, these two reactances cancel one another, and the only thing limiting the current in that circuit is that resistance. That's going to be an important concept when we discuss series RLC resonant circuits. Two important observations. The resonant frequency and the impedance of the circuit is purely real at that frequency. Page number 232, this frequency f sub 0 or omega 0, at which the impedance of the circuit is purely real, is known as the resonant frequency. And the circuit itself is at this frequency is said to be in resonance. Resonance is a very important consideration in many fields of engineering. For example, engineers designing the attitude control system for the moon landers had to ensure that the control system frequency did not excite the body, causing bending or resonant frequencies of the vehicle, of the entire vehicle. Excitation of the bending frequencies would cause oscillations that, if continued unchecked, would result in a buildup of forces or stress until the vehicle would finally break apart. I mean, who hasn't heard of the disaster of the Tacoma Narrows Bridge, that because of wind blowing across the bridge caused the entire mechanical structure to resonate to such an extent that the bridge tore itself apart? The wind fluctuating at the frequency near the natural resonant frequency of the bridge, which they approximated to be 0.2 hertz, drove the structure into unchecked resonance until the bridge destroyed itself. And if you haven't seen the video, Google it. Take a look at the 2-minute video. However, resonance can be useful, such as providing string and wind instruments with added volume and rich tones. Other applications that take advantage of this resonance include measuring instruments, and there's numerous measuring instruments, sensing devices, sensors, and select frequency filters and detectors, one of which is referred to as tank circuits, or simply tank circuits. Series resonance example, or series resonant example. What I'd like to do here is I'd like you to cover up that bottom part of page number 233, because just knowing what you know for the equation of resonance, resonant frequency on the previous page, and just what we've covered in the preceding chapters, you should be able to do this. You should be able to work this out. So I want you to find the resonant frequency, both in terms of hertz and radians per second. I want you to find the phasor current in that circuit. It's a series circuit. Find the phasor voltage across the resistor, find the phasor voltage across the inductor, and find the phasor voltage across the capacitor. I want you to stop the video, take a minute. It doesn't take long. It's going to take you 5 minutes, less than that, to work these out. If you did that, and I hope you did on your own, this is the solution. There's the solution. I calculated the resonant frequency in hertz, approximately. I rounded it off to 5 kilohertz. The resonant frequency in radians per second was 31.6 K radians per second. And then at resonance, the X sub C value is equal to 3160, and I rounded it off, or you're going to have round off error here, so don't worry about the round off error because of the 2 pi, depending on how far you take this out. I think I used 2 pi as 6.28. That's a close enough approximation for pi. So So I ended up with the capacitive reactance of negative 3,160 ohms, and I ended up with the inductive reactance of plus 3,160 ohms, and they should come out to be equal because the resonant frequency defined that. Here's what I get for the current, 50 milliamps in the circuit at an angle of 0, because it's purely real, because all we have is that resistor. All we have is that resistor up there, because these canceled one another out. So we have 50 milliamps. I want you to notice that the voltage across the resistor drops the entire source voltage, 5 at an angle of 0. But I want you to notice something that's pretty important. The resonant voltage rise due to resonance for the inductor and the capacitor are 158 volts at an angle of 90 degrees and 158 volts at an angle of minus 90 degrees. And that's what you would have calculated. You didn't make a mistake doing this. If you work this out the way I told you to, this is what your engineering analysis would have told you. Notice that all of the source voltage is dropped across the resistor. Okay, no problem there. Also, of course, the voltage across the inductor and voltage across the capacitor are equal in magnitude but opposite in phase, which they should be. This causes these voltages to cancel, making the total reactive voltage 0. So if we take a look between this point and this point, the voltage is 0, because Kirchhoff's voltage law has to hold true. This rise has to equal this drop. And then between here and here, it has to be 0. But what about the individual element voltages? Wow. Let's read this again. This causes these voltages to cancel, making the total reactive voltage 0, but causes a dangerous individual resonant voltage rise across the individual reactive elements. We only have 5 volts up here, peak. And we're ended up with 158 volts individually between this point and this point, or this point and this point. Very important observation. Some strange things can happen at resonance. So we have to be careful having a lab that would illustrate this, obviously. We don't want anybody getting hurt. What about quality factor? I want to define quality factor. The quality factor Q is a dimensionless quantity that measures, in general, the quality of a capacitor or an inductor. The smaller the resistance value, the better the element. So where does the resistance come from? Well, the resistance is really in a coil. The resistance is the distributed resistance in the windings. It's very small, but it plays a part. So the way I modeled it in this example down here is this R here of 159 ohms, and that's what that is. Let me hold up so you can see it. In this example down here, I have R is equal to 1.59 ohms, and the inductor is equal to 0.02 henries, and the capacitor is equal to 1.27 microfarads. Notice I put a dashed line around this because I'm defining a Q here of this circuit. And for sake of illustration, I'm not defining a Q with the capacitor here. I'm just defining it just here with this circuit. I'm pulling out the resistance down here, and I'm pulling out the resistance here, and I'm lumping it all up here. Now I know I show that as dotted lines here, but I want you to picture this resistor here just being the dielectric resistance here. Well, that's not true. That's not true. In this case right here, the way I have this shown is this dashed line around here just pulls this resistance and these windings out. If you go back up to the top here, I define Q a couple different ways. Q is equal to the inductive reactance over the resistance, which is also equal to the capacitive reactance over the resistance in the circuit, which can also be written this way. So it depends what you have. If you have the inductive reactance and the capacitive reactance at resonance, these are the same equations here, same numerators. And over here, if you have resistance, inductance, and capacitance, you can use this formula. It can be shown that there is a resonant voltage rise across the series inductor and capacitor such that the voltage rise is equal to this quality factor times the source voltage, or the voltage across the capacitor is equal to the quality factor times the source voltage. Now, we didn't use these equations in the previous example, but you could go back to the previous example and you could calculate a Q, a quality factor for the circuit in general, using any one of these equations here. And we could, once you know that quality factor, you could use it to calculate the voltage across the inductor or the voltage across the capacitor. Those resonant voltage rises. You didn't even need to get into the current once you make this calculation up here for Q. Go back and take a look at that and see if those hold true. They will. And then I want you to take a look at this second example down here where I have this source voltage. I have the resistor, I have the inductor, and I have a capacitor. I want you to calculate the resonant frequency here, and I did. I calculated the Q of that circuit, and I did. It's considered a high coil Q. The higher the number, don't forget, the higher the Q, the better the element. So if you look up here, what's going to cause Q to go higher? It's a smaller resistance. Oops. The smaller this resistor, in either case, the higher the Q. And that resistor, I got off to a bad start when I defined the circuit here, but when that resistor is just the resistance in the RLC circuit. It's whatever that resistor is. And that resistor here is coming from the resistance of that windings, because that resistance current flows through in this circuit. Current doesn't actually flow through that dielectric. That's why we're not looking at that real high leakage resistance we talked about before. This is an AC circuit, don't forget. AC circuit, the only thing we're concerned about is where the current actually flows through, and it flows through that resistance here. So I just pull out that resistance, and it turns out that the smaller the value of R, obviously, the better the coil, and the higher the Q value. So I just go down here and I calculated the current in this circuit, and I used the current to define the reactive voltage rise in both for V sub C, which will be the same thing as V sub L. I'm just calculating one of them here, and V sub C using the Q factor. So I use both the current and the Q factor, and you see minus round off here, you get the same thing. But the purpose of running this exercise here is recognizing the fact that we have a 10 volt peak here, and this value of Q being so high, a high quality coil, 78.9 is considered high. Look at those voltages we end up with. And that takes us right back to this statement we have here. So for the quiz or the exam, you have to be able to find the resonant frequency, and you have to be able to find the resonant voltage rise across these individual elements. So I gave you 2 or 3 examples here that will give you a pretty good head start on what you'd be expected to know in the exam. And that concludes this lecture.